Welcome everyone. So this is our 28th live stream geometry, and I'm going to do the same contest as last time. So the Middle European Math Olympiad. So this is a really big competition between a lot of European countries. I think it used to just be Austria and Poland, but now it's 10 different countries. Let me look up what those 10 countries are. Hold on just a second. So the 10 countries are Austria, Croatia, Czech Republic, Germany, Hungary, Lithuania, Poland, Slovakia, Slovenia, and Switzerland. And they have both an individual contest and a team contest. So I picked problems from both. So with that, I will get started. So let me share my screen. Second. All right. So this is actually the website for the contest. So here's the first problem that I chose. So we have a quadrilateral ABCD. So that AB is equal to CD. So let me try it like this. Where's my compass? There's a compass. So AB equals CD, so D is some point on the circle, which I'm going to hide. And then the midpoint of the midpoints of the diagonals are E and F. And EF meets AB and CD at G and H. And we want to show that AGH equals DHG. That's interesting. So basically that means if we extend AB and CD, we get an isosceles triangle. So I'm going to try that, see if that works. Let me make some more room here. Oops, where did point I come from? What happens if I delete it? Whoops.
You didn't choose C.
I didn't choose C. Yeah, I chose point I. All right, so I will hide this and this. So yeah, my idea is I want to show that IGH is isosceles. And I know AB is equal to CD. It's kind of interesting. This looks a lot like the Gauss line configuration. So maybe I could also extend BC to meet AD.
It would be nice, I think. We can use it.
All right. Yeah, let's try the Gauss line. See if that works. So let's see, I can move point D around a little more. Let's try to make the figure look nice. Maybe something like that. So EF, so yeah, GH should pass through the midpoint of IJ using the Gauss line. Whoops. It's interesting. Oops. All right. So we want to show this is isosceles. Yeah, maybe we could use Menelaus. Let's see. So like if AB equals CD, we have JD over JA equals BI over IC using Menelaus. It's an interesting configuration. So yeah, we want to use that. So often, like when you have AB equals CD like this, it helps to draw the McKell point of quadrilateral ABCD. Let me try that.
Yeah, actually, it's the midpoint. Midpoint of AID, arc AID.
Yeah, this point right here would be the midpoint. Yeah.
And BIC.
And BIC. Is LIGH cyclic? No. Is IGH similar to LAD and LBC? I don't think so, but let me try it.
It must be.
Oh yeah, because they're all isosceles. Yeah, wait. L. Yeah.
Actually, I don't think it must be. IGH is similar to LAD.
LAD and LBC, yeah, it's similar to both of them. So maybe, But yeah, I feel like this problem, it seems so simple. It looks like there has to be a simple solution, right? Let's see. So yeah, how do we show IGH is similar to both those? Is there a way to use ratios? So yeah, we want to show like IG over GH is LA over AD.
Well, how do you use midpoints?
Yeah.
It's hard to use them.
Yeah, you have to use them somehow. Yeah, maybe the gliding principle. So what if, yeah, I'm not sure how helpful the Gauss line thing is actually, but we want to show, let's see. Yeah, I'm trying to use the gliding principle. So we want to show that so we know LBC is similar to LAB. Yeah, like what if I did this, for example? Let me try a couple things here. Yeah, maybe I could form parallelograms or something. Like if I label the midpoint of AB, yeah, let me undo some of that. Yeah, let me try drawing in some more midpoints. Like if I draw the midpoint of AD and the midpoint of BC, and I could even do it with these two also. But I think is MENF is like a parallelogram then, right? And maybe it's actually a rhombus. I think this is actually a rhombus because NE is half of AB and yeah, NE is half AB and MF is half AB. Yeah, so this is a rhombus right here. So MN is actually perpendicular to GH. And now I feel like we should be pretty close. Let me try something. And then this is parallel to this, and this is parallel to this, so I think it solves the problem. Ah, that's a fun solution. I like it. It's a very cute problem.
Actually, I didn't understand.
Yeah, sure. So let M be the midpoint of AB, and let N be the midpoint of BC. So then I claim that MENF is a rhombus.
Yeah, I saw that.
And yeah, and once it's a rhombus, so we know angle NEF is angle NFE.
Okay.
And then this is parallel to NE and this is parallel to NF. So this angle equals that angle. It's interesting. Does it make sense? All right, see, I'll write it up here. So let N be the midpoint of BC and N be the midpoint of AB. Yeah, I was gonna say, there's no way it could be that complicated of a solution. So
actually, we even don't need M.
We don't even need N. Yeah, you're right. We only need one of the two for the proof to work.
Yeah, we will just use NEF is isosceles.
Yeah. All right. So I will delete point M. So we have BN equals NC and AE equals EC. Means that NE is parallel to AB and NE is half of AB. Break that up into two lines. Oops. That's better. And then similarly, an F is parallel to CD. And an F is half of CD. which is the same as half of AB, which is ME. I'll just write it like this. So that means that angle NEF is angle NFE. And that means that angle BGH is CHG. Yeah, first I'll just write that. That means angle BGH equals angle CHG. And that means that angle AGH is DHG. All right, that was an interesting one. So yeah, the lesson is, yeah, when you have midpoints of diagonals, it helps to construct the midpoint of the side. All right, next problem. So we have an isosceles triangle with vertex C. I'm just going to do this. So call that A. And then this is B. So AC is equal to BC. And you draw the in circle of it. Let me draw a little bit of a taller triangle. Right. And I'm going to use this. There's the in circle. I'll just call I the in center. And it touches AB and BC at D and E. And then a line passes through A and intersects it at F and G. Okay. All right. And then EF and EG. Intersect AB at K and L. Oh, we've done this problem before. I'm pretty sure we've done this before on my channel. It's just projective geometry. So yeah, I'm going to write up the proof quickly, but I think it was a very quick proof. So maybe the other contest we did took it from this contest. I wouldn't be surprised. But yeah, it looks really familiar, and I think, yeah, we've done this exact problem. So yeah, the solution, and I think I actually memorized the solution, but it meets, so EF meets it at K, and EG meets it at L. And then this we could call, I don't know, J, let's say. So I'm just going to write it up quickly because, yeah, I've seen this before. So you do a projection. We want to show dk is equal to dl, which is the same as showing the cross ratio of ek or KLD infinity is 1. So if you project through E onto the circle, you would get DJGF. So we want to show DJGF as harmonic, but obviously it is because the tangents at J and D pass through GF or concur with GF. So
this was nice.
Oh, what?
This is a nice problem, actually.
Oh, I'm sorry, what did you say?
This is a nice problem.
Yeah. So we start off, so GJFD is harmonic. And that's since the tangents at J and B concur with FG. Okay. And so if that's true, then that means the cross ratio is -1. And then projecting through E onto line AB. We have K, L, maybe I'll write it like this, FG, DJ, that would make it better. KLD and AB, the point at infinity, is equal to -1. And if that's true, we know D is the midpoint of this implies that D is the midpoint of KL. So yeah, this means that all right. So that is a short one. And I'll move on to the next problem. This one's from 2016. This one looks maybe a little trickier. So ABC, it's an acute triangle with circumcenter O. All right. Oops. P lies in the interior so that APOB is cyclic. And BP is, okay, so let me draw the circumcircle AOB. P is such that BP is perpendicular to CP. One sec, Serdar, I'll be right back. All right, thanks for waiting. So let's see. So BP is perpendicular to CP. So basically, let's draw the circle with diameter BC. So this should be point P right here. And if we want BAC is greater than 45, I think that's greater than 45, but I'll check. Yeah. Okay. We want to show, okay, so that's point P. Q lies on BP such that AQ is parallel to PO. All right. This is point Q. We want to show that QCB equals PCO. All right. Let's see if there's something I can hide here. So I'm just going to make it look a little nicer so that it doesn't overlap the problem.
Can you name the point intersection of the circle with diameter BC and AB?
Yeah.
And let's OE cut the circum circle of AOB, yeah, this point.
All right.
Then CPF is collinear, are collinear.
Ah, okay.
I've seen a similar problem in Govaka.
Interesting. Oh, Gowaka. So is that the...
No, it's not so similar, but
okay. Don't say Gowaka is still going on, right? I think so, right?
Yeah.
So yeah, don't say too much about it. All right. All right, so we want to show angle QCB equals PCO.
This was just angle chasing, this collinearity.
Well, once you know they're collinear, it's just angle chasing.
No, this collinearity is angle chasing.
Okay, to show they're collinear. All right. Let's see. So do we want to find congruent triangles, similar triangles? Maybe we could use the isogonal line lemma. There's a couple of things we could do here. Maybe some median. Yeah, I see a whole bunch of different things here.
Actually, it's one way that we can prove BC, Q, and H are cyclic.
DCQ and
BCQ.
BCQ.
And H.
Where H is the orthocenter?
Yeah.
Okay. Oops.
If we prove that the rest is angle chasing, but maybe it's not helpful. I don't know.
Let's see. I don't think AP and H are, yeah. Did you like use isogonal conjugates or something to get that?
We have to show OCD equals to PCQ. And OCD is 90 minus A. So we have to prove that PCQ is 90 minus A. Then we have to prove that BQC is 180 minus A.
Interesting. So yeah, we want to show BQC is 180 minus A. Are P and Q isogonal conjugates? No, they're not, because angle ABQ isn't CBP. Let's see. I'm going to delete point H now, just because I think, like...
Yeah, it's not necessary.
Yeah.
Actually.
Like, we can just try to show that BQC is 180 minus A. I don't think FO and AC are parallel, but let's see. Yeah, they're not parallel.
Oops. What was that then?
Oh, so yeah, it just looked like that. So that it's not actually collinear then. Whoops. Wait a sec. I thought. Oh yeah. Okay. So they don't really meet on the circle, right? Yeah. I guess we just got. Yeah, you can see they don't meet. But yeah, whenever I see QCB equals PCO, there's a couple. So what if we try to use the isogonal line lemma? Yeah, I don't think that would work too well. Could we use some medians somehow? Let's see. Is CO a median in some triangle? Is CO? I wonder if I don't think O is the midpoint of FP, but I'm going to check it out. No. So saying that QCB is PCO, it's the same as saying that OCB is PCQ, right? And OCB is OBC. So we want to show that OBC is PCQ. It's interesting. Is PCO, hold on a sec.
I think we need to reflect Q with respect to P.
Okay. So let's see. So
we want to prove that PQ prime multiplied by PB equals to PC squared.
PQ prime times PB is PC squared.
Yeah.
I don't think that's true because that would just.
Yeah, right. Can you change the shape to see whether Q prime is on circle?
Yeah, Q prime is definitely on the circle. Let's see, is that must be. Yeah, it is interesting that Q prime lies on the circle. Is Q prime like the ortho? I guess if we could show that Q is like the orthocenter of a triangle, that would mean that Q is the orthocenter of triangle B up C. because the reflection over it lies on the Circum Circle. It's interesting. So Q is actually the orthocenter of BFC. How do we prove that? So, but yeah, suppose we knew that. So then QCB, that's like the orthocenter of this triangle, and PCO, yeah, I feel like it would probably be just PCO is the same as FCO. So yeah, if we can show that Q is the orthocenter of triangle BFC, that would solve the problem. And yeah, then we wouldn't even really need point Q prime, although maybe it might help to prove that Q is the orthocenter. So yeah, I'm thinking like, yeah, where do we use that this passes? So we want to use that OF is equal to OB. I'm sorry, we want to use that OA equals OB. AQ is parallel to PO. Let me draw the center of this circle right here. I'm just curious. Let's see, I don't even know what circle this is. Circle D. Okay. Is HP tangent? I'm just guessing here. No. Yeah, I'm going to delete Q prime for just a sec. I might add it back later, but let's see. So we have triangle ABC, O is the circumcenter. This intersects at P. Those two circles intersect at.
We couldn't use parallelity.
Yeah, we haven't used that AQ is parallel, or that AQ is parallel to PO, right? Yeah, we just want to show that Q is the orthocenter of BFC. That's also the same as saying that C, Q, and G are collinear, right?
Actually, I think AP equals to PQ. Can you check it?
Ah, interesting.
It is angle chasing just.
Ah, okay.
It is well known that PO is angle bisector of QPA. X angle bisector.
The
Because
external.
OA equals to OB.
Okay. So since OA is equal to OB, then OP is by an angle chase, the angle bisector BOA. So it's
No,
also
BPA. X angle bisector of BPA.
BPA
Yeah.
by an angle chase. So therefore it's angle bisector QPA. And so there.
So we know that QP. Can you extend AP?
Yeah.
So we know that PQA is half of QP extension of AP.
Okay. Yeah. Okay. So yeah, like yeah. So we know QPA is isosceles, right? From that. All right. So if we know QPA is isosceles, well, yeah, actually, then maybe Q prime is good to add, because if QPA is isosceles, basically we want to show angle QAQ prime is 90. Wait, is angle Q, let me check this. OQA 90? No.
Actually, we know that Q prime is 90
How do we know that?
because AP equals to PQ equals to PQ prime.
Yeah,
Because
okay. But yes, okay, so then we'd have to show Q prime lies in the circle. But yeah, if we define Q prime that way as the reflection, yeah, then we know it's 90 degrees. I wonder if we can like rewrite this problem. Like, what if we start with triangle BFC, and then we let Q be the orthocenter, and then we let P and G be the phi to the altitudes. Where would I go from there? Oh, O would be the circumcenter of the triangle. Okay, and then the parallel through OP.
I think we need to extend AQ to use 90 degree.
So that this is like the, what do you call it, the antipode? Is Q prime O tangent to the circle? No. But yeah, you're saying like extend it to this point right here, right? Let me move it just so it doesn't look like it's tangent. It's hard to make it look like it's not tangent. Oh well. But yeah, I feel like it's like, what if we start with triangle BFC? Q is the orthocenter and O is the circumcenter, and P and G are the phi of the altitudes. We then draw the parallel through H to OP. It meets the circumcircle at A.
Actually, we didn't prove that Q prime is on circle.
Yeah, we had. If we did prove that, it would solve the problem. That's the thing.
Yeah.
Yeah.
So drawing this is meaningless. I think we have to delete.
No, I agree. Let me think about this. So I kind of like, I'm thinking, I'm rephrasing the whole problem so that instead we want to.
I solved it, I think, because PO bisects A Q prime.
Okay. OP is the perpendicular bisector of A Q prime. Is that obvious?
Because AP equals to PQ prime and OP is X bisector, X angle bisector.
So Q prime has to lie on the circle. Okay, yeah, that does it. All right, so
I said Q prime is on the circle.
Yes. Okay. So, all right. So let me write this up. Okay. So, yeah, and then like the way I would finish it is, yeah. So once so like you just prove that Q prime lies on the circle. So that means that Q is the orthocenter of BFC because the reflection of it over FC lies on the circle. And so if that's true, then O and Q are isogonal conjugates, obviously. So QCB is FCO, which is PCO. It's pretty nice. All right, so did we even need point E? I'm not sure if we did.
We didn't.
Okay. Well, wait. OP is parallel to AQ. So the reflection of A over yeah, I wonder if yeah, so once we know that this is isosceles, once we know that this is isosceles, and yeah, this is the external bisector, then by symmetry, it has to, like the reflection, like, yeah, it just has to be true by symmetry. So yeah, I'm going to delete point Q prime for now. And then I'm going to add it back in when I do the proof. So yeah, and I don't think we need point G either. Okay, so first we're going to show that APQ is isosceles. Yeah, I'm going to delete D also. Whoops. I want to do that. So to show that APQ is isosceles, we want to show basically that angle QPO is the same as so we know QPO is the same as AQP, and QPO is BPO. Yeah, because arc BO is equal to arc AO. So angle BPO is angle OAP. So hold on just a sec. Or no, I'm sorry, BPO is the same as ABO. Just thinking through this in my head. So yeah, it must be an angle chase to show that APQ is isosceles. I'm just thinking about the best way to do it. So let me do it like this. So we have
OPB equals to OAB equals to OBA equals to OP extension of AP.
Okay, I'll call it X for now. So we have OPB is OAB is OBA is OP extension. Okay, so if I just call this point, I don't know, I could call this point X, let's say, for now. OPB is equal to OPX. So by symmetry, the reflection of A over OP lies on the circle, and QP and that point are collinear. So I'll say let A prime be the reflection of the A over OP. And then by symmetry, A prime lies on the circumcircle of ABC. So let me draw that point. And then also QP and A prime would be collinear. With QP as PA prime. Is that off? Let's see. So once we have this,
once we have Q is the orthocenter.
Yeah. So I guess this. So I guess I left out a step. So this implies that PQ equals PA. Because OP is parallel to AQ. I'll just say that. And then, yeah, once we know that, so the reflection of Q over FP lies on the circle FBC. So we know that, and we also know that, I'll say over FC. So Q lies on the altitude from B. That implies Q is the orthocenter of BFC. BFC. And once we know that, therefore, angle QCB is 90 minus angle B, which is the same as angle OCB. So yeah, it's well known that Q and O are isogonal conjugates, but I'll just, yeah, so that means that I'm just going to write out the proof. Which is 90 minus half angle FOC, which is angle PCO. And that's it. All right. That was a nice idea to construct this part right here. So I think we've done enough with this, so I'll move on to the next one. All right. So we have a triangle ABC with AB greater than AC, and I is the end center. Oops. And AI, so the angle, the foot of the angle bisector is D. Let's draw it like that. D. Let P be on BC so that PI is equal to PD. That's interesting. So I think I got to do something like this. All right, so this would be point P. That's weird. And let J be the point obtained by reflecting I over the perpendicular bisector BC. All right. So we have like an isosceles trapezoid. So this is J. And Q is the intersection of the circumcircles of ABC and APD. This is weird. So this is point Q. And we want to show that angle BAQ equals angle CAJ. Whoops. Let me just test that out. Angle BAQ equals angle CAJ. Yep. That's the same as angle BAJ equals CAQ, right? So yeah, BJIC is like an isosceles trapezoid. So maybe we have, is BAJ similar to AQC? I don't think so. AQC looks a lot narrower of a triangle. But yeah, Q is defined in such a weird way. So yeah, we have spiral similarities like wherever we have so ABC and AP.
Can you extend AD
Yeah.
and QP?
So I think that, yeah, they meet on the circle, right?
Yeah, just an angle chase.
They meet at the midpoint of arc BC. Let's see. I think they do. Oh, they have to because AI is an angle bisector. Whoops. I'm going to add it back in point A.
Actually, now we can prove that CEQ is similar to BJA, I think. I'm not sure, but it's possible.
CEQ and BJA.
Yeah.
Let's see. So BJA is 158. That's 146. I don't think so. Is that, you said CEQ, right?
Yeah, it's not true.
But maybe CPE is.
No, CPE is similar to ECQ.
Ah, okay. Maybe BP. Well, no. Yeah, BPQ. I wonder, let me check something.
Oh, I realized that some similarity. Can you name the intersection of IJ and AB?
Yes, IJ and AB.
Yeah, we have to prove that AFJ is similar to AQC.
Okay, AFJ and AQC. All right.
We know that AFJ equals to AQC by an angle chase, but we do not know more.
All right. Interesting. So angle ACQ is the same as angle AJQ. Wait, are you sure about that? Let me check. Oh no, ACQ isn't AJQ. It's ACQ is AEQ. And we want to show AEQ, which is IEQ, same as AJI. We could, yeah, let me draw this circle. Ah, I forgot about that. J lies on this circle by symmetry. So BJIC is cyclic. with center E. I wonder if, no, I was going to say maybe AB, maybe this is the midpoint of arc BC, but it can't be. Okay, so we want to show AFJ is similar to AQC. So angle AJI, it's angle AJE minus angle IJE. I don't know if that helps. Let me try drawing the line CQ. The CQ, I don't think it's parallel to AE. No. But yeah. Yeah, we want to show a spiral similarity takes ACQ to AFJ. I guess another way of saying this is see, hold on a second. So I think AJEG is cyclic. Yeah. What if we let IC meet AQ? No, I don't think that does much. I feel like maybe it's natural to let AJ meet the circle. And then we want to show that QG is parallel to BC.
We couldn't use the definition of P.
So how's, yeah, we still haven't used that, that's right. We want to use that PI is equal to PB. Let's see. Yeah, I'm guessing that'll be used in some kind of angle chase. Is AIPC cyclic? No. So yeah, I'm trying to find similar triangles with it. So maybe IDC. IDC and ADC share an angle. Oops. Not sure how to use that.
Is JBF is similar to IPC?
JBF and IPC. Let's see. No, because JBF, this angle is the same as angle JIP. Oh wait. JBF and IPC. Why weren't those equal? Oh no, because JBF is equal to FIC, which is not IPC. Oops. So yeah, we could rephrase the problem. Like, so we could start with two circles. Like, so BJIC is a trapezoid. Think about this. I feel like we could redefine the whole problem, and so that the problem is to show that PI equals PD. And let me think how we would do that. So angle PDI equals angle QPC. Which is the same as angle DPE. Wait, hold on a sec. No, PDI is AQ tangent to that circle? No. It's a hard one. I still like your idea of showing AFJ is similar to AQC. What if I drew the Circum Circle of AFJ? Or, yeah, the hard part's using that PI equals PB. Let me draw that circle in again. Does that pass through this tangency point? I feel like that's another thing that's just, yeah, that's not true. It's an interesting problem, though. I wonder. Yeah, we have to use some kind of isogonality theorem. you want to move on to the next problem for now and see and come back to this later?
Actually, I found something. We need to prove that EC over PC equals to F squared over VF multiplied by JF from length chasing. But we can continue and come later.
Okay, so you said EC squared over PC. Say that again. I wonder, is P? All right, I think I'll come back to this later, but that sounds interesting. Let's see.